Hi, my name is Jacob Shreve, and I'd like to demonstrate a project I've been working on called Access ML for machine learning. Access ML is a machine learning online portal, and it's meant to help physician scientists and other members of the scientific community incorporate machine learning into their research, especially if that individual does not have much of a programming background. Now, in order to demonstrate the scope and the usability of the website, I'm just going to jump into it rather than try to describe it. So if you go to access-ml.com, you'll be greeted with this kind of user agreement, just showing that this website is for research purposes only prior to our publication. Now, for data selection, normally you would be able to load your own data in, but because this is a demonstrative website at this point in time, you can just use our example data, and I'll submit that while we talk. All right, so you can see it's pre-processing. Now, I think it's important to point out that anything that happens on this website is happening in real time. Nothing was pre-compiled or pre-completed for demonstrative purposes, and so the times that you see throughout this demonstration are realistic of the times you'd actually have to wait if you're loading in your own data. Now, that sample data we're using here is from the University of Wisconsin. It's open source data. It's comprised of measurements from CT images of breast masses, as well as paired with post biopsy results, whether or not the mass turned out to be malignant or not. And so that is really similar to any kind of file you'd want to use for this type of application. Really, you have a target data, which is the first data column within your data set, and that says what you're trying to find, what you're trying to model. So now that our pre-processing is complete, you can see that our first column is our diagnosis column. The ones correspond to malignancy and the zeros correspond to benign. The remainder of the columns are simply the features, the measurements that are meant to try to predict the target column. Now, in this representation within our web browser, I've limited the number of rows to display to 100, and that's for the sake of memory within your browser. You can also increase it to 500 to demonstrate all of the data, but your results may vary. Now, we do have a quality control filter. Of course, our example data has passed. We have a tabulation of the number of rows. It also breaks it down by the type of feature, whether or not that's a categorical feature like the diagnosis column or a continuous feature like the rest of the data in this example set. Now, because we have no missing data cells, we also have no rows that contain missing data. And then we just have a demonstration of the total number of cells. So of course, this is just a brief data preview, but now we can go into some of the exploratory data analysis. So we begin with univariate analysis. You can see that each one of the columns are broken down according to some of the simple univariate statistical methods, such as the mean, the standard deviation, as well as the quartiles. Now we get to bivariate analysis. This is a graphical representation where we can pick any two columns and compare them to each other. So here we see we have diagnosis versus the radius mean. Then we can reset this and then we can choose something else. So why don't we choose the diagnosis versus the concavity mean. And then these images will refresh. So these were just generated on the fly. And then of course we can always look at a higher resolution version of these that are publication quality. Going back to our data analysis page, if we scroll down, we can see that when we're looking at these different columns, they are color coordinated. The blues are for categorical data and the greens are for continuous data. And you can see that if you're looking at categorical information, it will list the categories. So here there's only two choices, ones or zeros. And if we're looking at continuous data, it will list the entire range. So the range of all radius means found go from 6.9 to 28. And finally, we have a multivariate analysis, and this is going to be an all versus all compilation of bivariate analyses. And so you can see that you can look for trends within the data in a multivariate manner. Okay, so finally we can go to the heart of the program. It's the analysis. Within the analysis section, the most important thing is to try to understand how we can apply machine learning algorithms to the data set. To assist with this, I've broken down machine learning algorithms into a few different classifications. We have supervised learning that's using a classifying method. We have supervised learning that's using a regression method. We have ensemble learning that's bagging, and we have ensemble learning that's boosting. Now, of course, each of these have different parameters that you can explore. So XGBoost, you can change the learning rate, the max depth. These are kind of power user things. But in any case, if you'd like to explore the data, you can simply select all, and then you can compare. Okay, now in the background in real time, we are now applying all of these different machine learning algorithms to that example data set that we loaded. It's going to take just a few minutes as it goes through each one of these algorithms, but in the end, it's going to create a rank order list of the algorithm's performances. So each of these algorithms may model the data to different degrees of efficacy. And we're going to then explore which worked the best. Okay, so here we have a new graphic. This is a rank order plot of the different algorithms, and this is based on the area under the curve for the receiver operator characteristic. So basically, this is just looking at an evaluation of the confusion matrix, specifically weighting the true positives and the false positives. And you can see that for this data, we do have a high scoring mechanism here. So LightGBM, linear regression, and random forest all did pretty good. But if you look at LightGBM, it's a nice play between the specificity, sensitivity, and AUC, and you lose some of that with linear regression, especially the sensitivity. So why don't we explore the LightGBM more as an example? I'm going to skip down here until we get to LightGBM again, and you can see it's right here. So now you'll have a summary of the parameters that we use to run the model, and then you're going to have a summary of the confusion matrix statistics. And then you have a receiver operator characteristic, and this is user definable. You can also save images and things for publication, and it prints the AUC. Now, something very important, I think, for any of these machine learning algorithms is understanding what drives them so that they're not a black box. For that, we have the interpret panel. Let's go down to LightGBM. Now, these are graphics that were just created at the same time that our models were trained. There's 3 graphics. I'm just going to open the higher resolution versions of these so that we can take a closer look. Okay. Now you can see that these are made with Shapely Statistics, part of the SHAP package. And what we're seeing is that these are the different features that are driving the model, and they're scored according to the importance that they were found to have for making the model itself. So we just have a bar chart in order of progression. Even more telling is this representation of the data, in which every single data point from the example set is plotted against each of the features. And you can see that things in blue actually have low impact on the model, things in red have high impact. And if you see that vertical axis there, to the left of the axis is actually driving the model towards benign, and to the right of the axis is driving it towards malignant. And so you can see a better breakdown of how each of those different features interplay. And finally, we have this representation, which can be thought of as a collapsed version of the previous image we were just looking at. Okay, now going back to our analysis tab, the point of this website is to take data and understand how machine learning algorithms can model that data and predict outcomes. Thus far, we've demonstrated how we can apply all these different algorithms to a data set, evaluate the different models that are created, and then interpret those models by looking at how the features created that model. But the point of machine learning is to use previous data to understand how to predict future data. Now let us implement that here. We uploaded the previous example data regarding breast CT measurements to predict malignancy versus benign tumors. You can see that LightGBM did a good job predicting those outcomes. And if you scroll down here to our LightGBM entry, you can see there's something that says generate and launch a prediction server. Let's click that now. Here we see that we have a customized machine learning real-time prediction server. What has happened was that the model that was created in order to be evaluated by LightGBM was captured and saved on the server in a de-identified manner that is now implemented on this personalized website. Now, this web address that was created for this prediction server is now static, which means it's going to be living on the server unless it's deleted, meaning that this website, this prediction server, can be revisited again and again or distributed in order to use the model that was previously trained. Now, I will say I think this is very important, especially when trying to publish, because if you create machine learning algorithm models that are meant to be used in a research setting, they need to be distributed in some way, and that could be very daunting to do if you don't have programming experience. The goal of AccessML is to allow a user to upload their data, do basic exploratory data analysis, and then apply each of the commonly used machine learning algorithms to their data to understand which could be most efficacious at creating a good model. Now, once that's modeled, you can look at the features and understand the weights and importance therein. And then finally, create a real-time prediction server so that new data can be explored and classified by that model. So you'll see that right now for the real-time prediction, it's empty because we actually haven't done a prediction on the server yet. And underneath technicals, there are bits of information to give the model provenance, including the original training data metrics, the confusion matrix, the parameters used to train the model, the comparison to the other machine learning algorithms at the time that the model was created, and also the feature weights from the model creation. Okay, and as a demonstration, I will just put in some random data, and then we can submit the data. The data will actually be confined to each of the features' minimum and maximum parameters, and you can see that the target prediction is going to be 0. Now, this is because there is a 22% chance that the prediction is 1, and because it's less than 50, it's going to be called a 0. And it creates new figures as well. Now, these are individualized features for this particular individual that has been loaded into the model to show how these weights went into creating this prediction. And that concludes the demonstration of Access ML. I think there are still many exciting features to be added, including additional machine learning algorithms, more feature generation, and more in-depth model evaluation, to name just a few. And so I'll be pursuing grant support to aid in this endeavor, and I hope to publish the software as an open source resource for the scientific community. Thank you very much for your time and interest.